Welcome to this explainer. Look, if you've ever built a system that relies on large language models, you know the dream. You ask for structured data, and the model perfectly hands it over. But the reality? You ask an LLM for JSON, and you get JSON, most of the time. And in production, most is exactly the problem. Today, our ultimate goal is to completely transform that frustrating hurdle of unreliable outputs into a perfectly solved, mathematically guaranteed problem for your production systems. We're talking about constrained decoding. Okay, let's dive into this. Picture this scenario. You're building a classifier. You prompt an LLM to return one of positive, negative, neutral. You wait for the API response, and instead of a single clean word, the model gives you a conversational paragraph. The sentiment is positive because the customer explicitly states, and boom, your parser crashes. Your downstream pipeline just completely halts, and your classifier's F1 score instantly drops to 0.0. It's a visceral, deeply frustrating pain, and honestly, it's usually the exact moment an AI engineer considers changing careers. And all of that pain really happens because of one simple truth. Free-form generation is not a contract. It is merely a suggestion. You can ask the model nicely, you can beg it in your system prompt, but production systems do not run on polite suggestions. They absolutely need hard, unbreakable contracts. And that perfectly sets up the massive difference we're looking at today, the difference between asking an LLM nicely and mathematically forcing it to comply. So here's our roadmap. 1. The problem with most. 2. How constrained decoding works. 3. The 2026 tool stack. 4. The speed paradox. 5. The field order pitfall. And 6. Choosing your solution. Section 1. The problem with most, and the 3 layers of 2026. Let's look at why older approaches are kind of falling apart when push comes to shove. Right now, you essentially have 3 layers of options. Layer 1 is prompting. Just asking nicely. You say, return only the JSON object. The reality? That only works about 80% of the time on frontier models, and it constantly fails on smaller open-weight models. Layer 2 brings us native APIs, like OpenAI's response format, Anthropic's tool use, or Gemini's JSON mode. These are super reliable, but you're completely vendor-locked. Which brings us to Layer 3, constrained decoding. This approach modifies the actual logics at every single generation step to guarantee 100% valid construction. It is literally the only way to get absolute certainty on any local model. Section 2. How constrained decoding works. The mechanism breakdown. Now, what's really interesting about this is the actual math operating under the hood. Think of this linear process like a really strict nightclub bouncer. At step 1, for every single step of generation, the LLM produces a logic vector across its entire vocabulary, which is usually around 100,000 tokens. Normally, it would just pick the likeliest one. But at step 2, our bouncer steps in. The logic processor checks the grammar's guess list. If a token is invalid, according to your schema, the processor instantly turns it away by masking its probability to negative infinity. By the time we hit step 3, the sampler's door, the softmax function can only possibly output a guaranteed valid continuation. The invalid tokens never even had a chance to get in. To cement that technical learning, let's look at the formal definition. A logic processor is simply a function sitting right between the model and the sampler. It computes which tokens are valid given the current position in your target grammar, whether that's a JSON schema, a regex, or a context-free grammar, and it completely masks the rest. It rigidly enforces your rules at every single step, making invalid output quite literally unreachable by the math. Section 3. The 2026 tool stack and implementations. So how do we actually implement this bouncer mechanism in our code? You have a few main paths. First are the native APIs. These require zero local management and give you server-side constrained decoding. But again, you're vendor-locked. Contrast that with a fantastic library like Instructor. Instructor is great for cross-provider portability using Pydantic, but it doesn't actually touch the logits. It relies on formatting prompts and using costly retries when the validation fails. And then you have tools like Outlines and Xgrammar. These are the engines that actually jump in and modify the math for guaranteed 100% validity by construction on your local models. And within those mathematical engines, you basically have 2 distinct flavors, FSM versus CFG. Outlines compiles your schema into a finite-state machine. That means every token gets a lightning-fast O1 lookup, which is absolutely perfect for flat schemas. But recursive schemas have to be flattened. On the other hand, Xgrammar and LGuidance use context-free grammars. These engines can handle complex tree-structured outputs, like nested comments, with near-zero overhead. And a fun fact for you. OpenAI actually credited LGuidance in their 2025 structured output implementation. Section 4. The speed paradox. Faster than freeform. And this brilliantly illustrates a massive, pattern-breaking plot twist about system latency that catches almost everyone off guard. Mathematically constraining the model, forcing it through a rigorous bouncer at every single step, actually makes it run faster than letting it generate freely. It's a completely counterintuitive reality. You would really think that adding all these intensive checks would slow things down, but it just doesn't. Let's demystify why that is. There are two main reasons. First, constraining the output drastically shrinks the next token search space the model actually has to evaluate. But second, and honestly more importantly, clever implementations simply skip token generation entirely for forced tokens. If your schema demands the scaffolding of a JSON object, say an opening brace, a quote, the word name, another quote, and a colon, the engine knows every single byte of that is completely deterministic. It doesn't even ask the model to generate those, it just fast-forwards and injects them. Section 5. The field order pitfall. The golden rule. So the crucial point is understanding some survival tips for real-world application, because this one will save you hours of painful debugging. Schema field order is logic, not just formatting. It leads to a trap called premature commitment. If you force the model to output the answer field first and the reasoning field second, the model commits to an answer before it even gets to think. It'll produce perfectly valid JSON, but the answer will be completely wrong, and no validation tool is going to catch it because the syntax is flawless. Always, always put the reasoning field before the answer field. Let's rapid fire through a few other major pitfalls. If you've got recursive schemas, remember they limit FSMs like outlines, so use CFGs instead. If you have a huge 10,000 option enum, compiling that will literally time out. The trick? Predict the top candidates with a retriever first, then constrain to those. If your grammar is overly strict, like forcing a precise date format when the data is just missing, the model will compensate by inventing a fake date. Always allow nulls or sentinels. And lastly, relying on pure vendor JSON mode without providing a strict schema is dangerous. It guarantees valid JSON syntax, sure, but not valid data for your specific use case. Section 6. Choosing your solution. The decision matrix. Let's move to and see how this builds into the ultimate payoff. This is your practical 2026 decision framework. I highly encourage you to take a screenshot or pause the explainer right here so you know exactly which tool to reach for in your own code bases. Let's walk through it. If you're using a frontier model from OpenAI, Anthropic, or Google, with a simple schema, pick a native vendor structured output APIs. If you need a workflow across any provider using Pydantic and your latency can tolerate retries, Instructor is the way to go. If you're running a local model and absolutely need 100% validity for a flat schema, Outlines and its FSM is your best friend. For a local model with a recursive schema, reach for Xgrammar or LLGuidance. If you've got a self-hosted inference server, lean on LLMs guided decoding. And if you're doing massive batch processing where retries are totally fine, pair Instructor with the absolute cheapest model you can find. To wrap up today, I want to leave you with a hard, provocative exercise. Now that you know that freeform generation is just a suggestion and that you can mathematically force the model's hand, can you implement a regex-constrained decoder entirely from scratch for a simple phone number? Could you write the logic yourself to track the state, compute the valid tokens, mask the logits, and verify absolutely zero invalid outputs across the 1,000 samples? It is an incredibly powerful concept to master. I highly encourage you to open up your IDE right now and try building a simple finite-state machine yourself. Thanks so much for joining me on this deep dive, and happy building!